Let's look at intermolecular forces. As the name would suggest, intermolecular forces are the forces between molecules. A molecule is held together by covalent bonds, and the covalent bonds themselves are intramolecular forces, or the forces within molecules. And so intermolecular forces are important because they tell us what are the forces between molecules that hold them together in the various states of matter. When we were talking about ionic and covalent bonding, we learned that melting point is a good way to evaluate the strength of chemical bonds. So the stronger the chemical bond, the higher the melting point. So here we have some pure metals and some ionic compounds with their corresponding melting points. And we can see here that in general, ionic bonds are stronger than metallic bonds. Now this does not mean that some metals have higher melting points than some ionic compounds, but on average, we find the ionic bonds to be stronger than metallic bonds. Again, what holds covalent compounds together are not actually the covalent bonds, but they're the attractions between molecules, or the intermolecular forces. And intermolecular forces are the attraction between molecules that are weaker than either ionic or covalent bonds, or for that matter, metallic bonds. And yet they are the primary thing that will hold a covalent compound together, which is why, in general, covalent compounds tend to have much lower melting points than ionic compounds. There are three categories of intermolecular forces. We have them listed here by type, and they increase in strength from top to bottom. The first one are dispersion forces. And dispersion forces are really exist between all molecules and atoms, but they are the primary force responsible for holding together nonpolar molecules. Polar molecules are held together by what we call dipole-dipole interactions. So you think back to our polarity unit and identifying the separation of charge on a polar molecule. The dipole is just the positive and negative side, and those tend to attract one another and create forces within the molecules that hold the molecules together. And the last one is hydrogen bonding. Hydrogen bonding is a special case of dipole-dipole interaction where you have hydrogen bonded to a highly electronegative element. And what that does is when those electrons are kind of pulled towards that electronegative element and away from hydrogen, what's left on one side of the molecule then is just a bare proton without much electron shielding, which creates an incredibly strong positive charge on one side of the molecule, and so you get really strong intermolecular forces. So let's, when we look at these collectively, they're often referred to as van der Waals forces. So let's look at them one at a time. I'm actually going to start with the dipole interactions. They're pretty straightforward to kind of see what's going on there. So here we have a molecule that's got a positive side and a negative side. And so what you have is an attraction from the positive to the negative, and an attraction from the negatives to the positives of the different parts of the molecule. These are permanent attractions and repulsions that will allow you to arrange the molecule to maximize the attractive force between things. And so these actually tend to hold together pretty well. And it takes a fair bit of energy to separate these molecules. And so that's the dipole-dipole interaction. It's the partial charge due to an unequal sharing of electrons that create permanent attractive forces that can align themselves to form a structure that is hard to break, takes a lot of energy. That's dipole-dipole interaction. As we said, hydrogen bonding is a special case of dipole-dipole interaction where hydrogen is bonded to a highly electronegative element. Often, you'll see those listed as almost certainly oxygen, fluorine, and chlorine. Sometimes nitrogen is involved in that. It depends on definition of highly electronegative. And what you get there is you get a very strongly positive side to that molecule because of that bare proton. And so these things are going to align themselves so the negatives are always in a position to be attracted to that positive charge and to create an attractive force, which is even harder to break than the standard dipole-dipole interaction. Now let's go back and look at dispersion forces. So here we have a couple of atoms of helium, 2 protons in the nucleus, 2 electrons in the electron cloud. those electrons are going to be attracted to the nucleus, or the electrons of one atom are going to be attracted to the electrons of the nucleus of another atom, fairly weakly because there's some electron shielding there. But they're also going to repel electrons in the electron cloud of neighboring atoms. And so you have this kind of extremely weak electrostatic attractions that hold these things together. And the thing about a dispersion force is that they are subject to constant change. The dipoles that get created in a nonpolar molecule are temporary. By that we mean by random motion, electrons in an atom might shift to one side of an atom, leaving that side more negative and the other side more positive. But as we see these attractive forces between electrons in the nucleus, of course, there are also electrostatic repulsion between electrons of neighboring atoms. And so if these two atoms on the right were to come in contact with one another, one or the other of those electrons might be forced away, or both for that matter. And what that's going to do is to create a shift in the electrons. And so now we have this kind of chain of electrostatic attraction that's going to hold these molecules together. But then if another molecule comes and bumps up, the electrostatic attractions can potentially create a chain reaction that would cause these forces to redistribute the electrons in that molecule. Okay, so let's look at the implications of this. We have three substances here, all with their melting points next to them. And if we start with methane, which, again, when we study three-dimensional structures, we know that methane is a nonpolar molecule. Because it's a nonpolar molecule, its dispersion forces are the primary force, and dispersion forces are extremely weak. And so the melting point of methane is all the way down at negative 182 degrees Celsius. That's all it takes to break the dispersion forces that would hold molecules together in their solid form at negative 182 degrees. That thing already has enough energy to break those forces. We know that ammonia is a polar molecule, and so notice we have over 100-degree difference in the melting point when you have dipole-dipole interactions. But again, this is a fairly small covalent compound, and dipole-dipole interactions are significantly weaker than ionic bonds. And so you still have pretty low melting points. Water, which has hydrogen bonded to oxygen, which counts as our highly electronegative element, has hydrogen bonding that holds it together. And again, that's a fairly big increase in melting points. Still a fairly low melting point because water is a fairly small molecule. On that note, size of the molecule will also affect the melting point because the larger your molecule, the more electrons there are to create dispersion forces. So if you have a large polar molecule, you have dipole-dipole interactions, but then also increasingly so dispersion forces are going to kind of inch that melting point up a little bit. Another thing to talk about real quick is there are some compounds that have large structures of covalent bonds. And as we've said, covalent bonds are extremely strong. It actually takes a lot of energy to break a covalent bond. The reason covalent compounds have such low melting points is because you're generally not breaking covalent bonds when you're trying to melt a covalent compound. You're breaking intermolecular forces. But in structures that are referred to as network covalent solids, the entire structure is made out of covalent bonds. Probably the most well-known example of this would be diamonds. So here you have an image of an uncut diamond here on the bottom right, and the molecular structure of that is just an interlinking set of tetrahedrals of carbons bonded to carbons. They create this incredibly strong structure that requires an extremely high amount of energy to melt a diamond. So if we want to go through kind of the summary of this, in order of increasing strength of chemical forces, covalent bonds are the strongest in general, then ionic, then metallic, and then your intermolecular forces are even weaker than the metallic. And within the intermolecular forces, right, we're talking about hydrogen bonding, dipole-dipole interactions, and dispersions from strongest to weakest intermolecular force. What does that mean for melting points in compounds? Well, network covalent solids are going to have the highest melting points. Ionic lattice structures or ionic solids will have the next highest melting points, then metals and alloys, then polar covalent, then non-polar covalent. If we want to take a look at some of these melting points, notice we have on the top here ionic compounds, then we have a few metals, then we have some covalent compounds, and notice the kind of gradual decrease in melting point there. Again, we have we have CH3, that's going to be a non-polar covalent. We have a polar covalent with formaldehyde. We have a hydrogen bonding in water. And at the very bottom, you can get a look at those network solids and look at the melting point of diamond at 4,027 degrees Celsius.